Just about every one of us has played with magnets at one time or the other. Remember the surprise and wonder you felt the first time you saw magnets in action? It might have surprised you even more to know that the Earth itself was acting like a giant magnet. The Earth is a bit unique in this regard. Of the 4 inner planets, Mercury, Venus, Earth and Mars, only our planet has a substantial magnetic field. It is not very strong, at approximately 100,000th of a Tesla. But even at this low a strength, this field not only makes a compass useful, it has many other benefits as well. It acts like an invisible shield that diverts and captures dangerous high-energy charged particles flowing constantly out of the sun, and is responsible for these spectacular light formations called the aurora borealis. Why do we have a magnetic field though? Our present understanding tells us that this field originates from the movement of molten ionized metal deep in the Earth's core. This is called a convection current, where hotter metallic fluid rises from the bottom and cooler metallic fluid near the mantle sinks to the bottom. This constant movement of charged fluid generates a magnetic field. Remember, whatever the scale, magnetism always arises from charges in motion. But what does this field look like? We can visualize this field by imagining a huge, absolutely enormous bar magnet buried inside the Earth. The south pole of this magnet is located near the geographical North Pole, and the North Pole of this magnet is located near the geographical South Pole. The axis of this imaginary bar magnet isn't exactly matched with the axis of the Earth's rotation. The two are tilted with respect to each other by about 11.3 degrees. Also, just as the geographical North and South Pole are linked by geographical meridians, the geomagnetic poles are also linked by magnetic meridians. Now, there is some confusion regarding how we name the Earth's magnetic poles, so bear with me. The pole near the North Pole of the Earth is called the North Magnetic Pole, but it behaves like the South Pole of a bar magnet. The pole near the Earth's southern geographical pole is called the Southern Magnetic Pole and behaves like the North Pole of a bar magnet. This is why when we use a magnetic compass, the North Pole of the compass needle is pulled towards the geographical North and vice versa. The pole near the North Pole of the Earth is the North Magnetic Pole, but it behaves as the South Pole of the bar magnet. The pole near the Earth's southern geographical pole is called the Southern Magnetic Pole and behaves as the North Pole of the bar magnet. This is why when we use a magnetic compass, the North Pole of the compass needle is pulled towards the geographical North and vice versa. Now, what are the elements of the Earth's magnetic field? We are not referring to things like nickel or iron here. We had discussed earlier that the magnetic field line tells us the strength and direction of the magnetic force exerted at any given point. The Earth's magnetic field can be resolved into various components or elements, and understanding them is important to land navigation and using a compass. These elements are the angle of declination, the angle of dip or simply dip, and the horizontal component of Earth's magnetic field. If you were standing at any point on the Earth's surface, the longitude passing through that point would tell you the geographical north-south direction and the location of true north and true south. Now think about this. The compass magnet or the needle does not really care about the actual location of the north and south geographical poles. All it does is point towards magnetic north. So, the magnetic meridian passing through a point is at an angle to the geographic meridian passing through the same point. This angle between the magnetic north and true north is called the angle of magnetic declination or simply declination. This mismatch between the magnetic and geographical directions is the lowest at the equator and the greatest at the poles. This is why a magnetic compass is almost useless once you get near the Arctic or the Antarctic circles. So whenever we are using a magnetic compass, especially when we are near the poles, we need to keep declination in mind. There is another effect that needs to be understood. It is called dip, and here is how it works. Think of a magnetic compass placed near a bar magnet. You will notice that the north and south pole of the needle align with the local magnetic field of the magnet, causing the needle to tilt. The closer you are to the poles, the more the needle tilts. And by the time the needle is at the pole, it is pointing almost straight down towards the pole of the magnet. Now imagine a compass on the surface of the earth. At any point, not only will the compass needle point towards the magnetic north, it will also tilt in the vertical plane. The needle on a compass like the one you buy at the store doesn't really allow this because it cannot move vertically. But if the needle was free to move up and down, it would tilt vertically more and more. This angle of tilt in the vertical direction is known as the dip angle, or simply dip. This is because at any point on the surface of the earth, the compass needle will react in response to two forces, the horizontal and the vertical components of the earth's magnetic field. If you were at the magnetic north or south poles, a free needle would point straight down or straight up. The vertical angles the needle makes at any given point on the earth is called the angle of dip. This angle will be maximum at the poles and the lowest at the equator. Remember, we are speaking about the magnetic poles and the magnetic equator. The third component we will look at briefly is the horizontal component of the Earth's magnetic field. As you can see in this vector diagram, at any point of the Earth, if you take a section of the Earth passing through a magnetic meridian, you notice that the force of the magnet or the force exerted on the compass can be resolved into two components, the horizontal and the vertical. And the angle of dip will depend on the balance between the horizontal and the vertical forces. The mathematical relation between these forces can be given by these equations. So we have ZE and HE, which stand for the vertical and horizontal components of the magnetic field. So the balance between these forces can be found by taking the tangent ratio, which is ZE upon HE. Now, let's dig a little deeper and understand the origin of magnetism in more detail.
Manorama Horizon, learning made simple.